Hello guys, let's continue our section on dynamics of fluid flow. On the previous sections we were discussing about an instrument, Venturi meter, and discussed about the discharge equation of a Venturi meter. Also gone through a problem for finding the discharge using a Venturi meter. Okay, now let's see a new device for measuring the discharge or rate of flow, and the device is Orifice meter. It's also a application of Bernoulli's equation. Okay, Orifice meter is a device used for measuring the rate of flow of a fluid through a pipe. It is a cheaper device as compared to that of a Venturi meter. See, it's also work on the principle as that of Venturi meter. It consists of a flat circular plate which has circular sharp edged hole called orifice and which is concentric with the pipe. Let's see the figure of a orifice meter. Then this is the figure of a orifice meter, and as you see here we have that orifice which has a smaller diameter as compared to the inlet, and this is called orifice plate. These are the plate which is mentioned here, the flat circular plate which has a circular sharp edged hole called orifice, and due to this arrangement we get a small orifice over here. Okay, see, we have two set of diameters. First one is pipe diameter and the second one is the orifice diameter, the diameter over here. This is formed due to the placement of this orifice plate. Okay, at two sections of this pipe we connect a E-tube differential manometer. Okay, this U-tube differential manometer is filled with a heavy liquid and used for finding the pressure drop H. Okay, by analyzing the figure we can see an area called vena contracta. Okay, it's an area of flow having a minimal area of cross section. See guys, in this figure the flow of fluid or the streamline flow is represented by these lines. Okay, see, after passing through this orifice the diameter of this flow or the area of this flow is reduced into a minimal dimension. Okay, and that point having a smaller area of cross section as compared to the previous area is known as vena contracta. We will discuss this term vena contracta in the following sessions. Now keep in mind a new term, vena contracta is an area of flow having a minimum area. Okay, the orifice diameter is kept generally 0.5 times the diameter of the pipe, though it may vary from 0.4 to 0.8 times the pipe diameter. That means the orifice diameter over here is designed in such a way that its diameter is 0.5 times the diameter of the whole pipe. It may vary from 0.4 to 0.8. Clear? And the diameter of this orifice can be varied by varying the length of this orifice plate. Clear? moving on to the discharge equation of orifice meter. The discharge equation of a orifice meter is shown here. The discharge Q is equal to CD into AO A1 into root 2H divided by root of A1 square minus AO square, where CD is the coefficient of discharge, which is a ratio between actual discharge to the theoretical discharge. See, AO is the area of orifice, area of the orifice, and A1 is the area of section 1. That means the area, the larger area over here. Okay. And finally H, which is the differential head. Both these equations are same. Please by heart any of this equation. Both are same. Okay. Discharge is equal to CD into AO A1 into root 2GH divided by root of A1 square minus AO square. Okay, moving to a problem. An orifice meter with an orifice diameter 15 centimeter is inserted in a pipe of 30 centimeter diameter. The pressure difference measured by a mercury oil differential manometer on the two sides of the orifice meter gives a reading of 50 centimeters of mercury. Find the rate of flow of the oil of specific gravity 0.9 when the coefficient of discharge of orifice meter is 0.64. Okay. First of all, let's list out the given values in the question. The diameter of the orifice is given as 15 centimeter. So, DO is equal to 15 centimeter. From this diameter, we can easily find the area of orifice. AO is equal to pi by 4 into DO square. Okay. Then we get the area of orifice as 176.7 centimeter squared. Clear? Then moving on to the diameter of the pipe. The diameter of the pipe D1 is given as 30 centimeters. Okay, obviously from this diameter we will find the area of the pipe. Equation for finding area of the pipe, A1 is equal to pi by 4 into D1 square, which gives area of the pipe as 706.85 centimeter squared. Also, the specific gravity of oil is given. SO is equal to 0.9. Then the next given value is the reading of differential U2 manometer X, which is 50 centimeters of mercury. Clear? For finding the differential head H, the equation is H is equal to X into Sg divided by So minus 1, where Sg is the specific gravity of heavy liquid. In this case, it's mercury, and So is nothing but the specific gravity of oil. Substituting the values, we get the differential head of oil as 705.5 centimeters of oil. Okay. Also, the coefficient of discharge of orifice meter is given as 0.64. Okay, then the rate of flow or Q or the discharge is given by the equation Q is equal to CD into AO into A1 divided by root of A1 squared minus AO squared into root 2GH. Okay, substituting the values over here, we get finally the discharge of the orifice meter as 137.414 liters per second. Okay, let's wind up this section and thank you.